we saw that to make the Dirac-Lagrangian gauge invariant, we needed to replace the covariant derivative by a gauge covariant derivative. In doing so, we introduce a coupling between the spin-off field and this new gauge field, mu, and the coupling constant is just E. And that gives rise to the interaction term of the QED Lagrangian. Mu is a gauge vector field we have introduced in order to restore gauge invariance. And it, of course, looks like very much the photon field, which we have as a mediator for the interaction between electrons in QED. Now that gauge invariance requires the presence of such a gauge vector field, we should have also a kinetic energy term associated to it. So it should cost energy to make it move in time. And we know from our experience with free vector field that this is, in the case of a massless field, just the Maxwell-Lagrangian. Of course, the Maxwell-Lagrangian needs to be also gauge invariant in order for this process to make sense. And indeed, by using the transformation we defined for the gauge vector field, we can easily show that the Maxwell-Lagrangian is indeed gauge invariant. But the Maxwell-Lagrangian only describes massless vector fields. What happens if we introduce a mass term to the field mu? We see we need to look at how the product mu transforms under gauge transformation. The gauge transformation is defined for any arbitrary alpha. Therefore, we see that in the general case, we don't have mu dash equal to mu. As a result, the gauge vector field cannot have a mass without breaking gauge invariance, and that's why it's the photon in particular, which is the gauge vector field for QED, is massless. We are now ready to write the complete version of the QED Lagrangian, where the interaction part between the spin-off field and the gauge vector field is contained into the gauge covariant derivative itself, and the kinetic energy part induced by the gauge vector field is in the Maxwell-Lagrangian, and there is no mass term in order to preserve gauge invariance. So to summarize, we started from a free theory for fermions, which was not local gauge invariant. We introduced a spin-1 gauge vector field. We replaced the covariant derivative by the gauge covariant derivative. We required the gauge vector field to transform in such a way that gauge invariance is restored. We added the kinetic energy part for the gauge vector field, but no mass term to the gauge vector field, which will break gauge invariance. So we did all that to restore the U1 symmetry, which gives QED as probably one of the simplest examples of gauge theory. But there are other examples of gauge theories associated with more complicated gauge transformation. And this is a case, for instance, for transformation belonging to the SU3 group, which are represented by 3x3 matrices, which are special and unitary, which give rise to the quantum chromodynamic theory, which is a fundamental theory for the strong interaction between quarks and gluons. In this case, the gauge vector field is a gluon field, which is also massless, as required by gauge invariance. So we have a well-defined gauge theory for electromagnetic interaction, which is QED. We have a gauge theory for the strong fundamental interaction, which is QCD. What happens in the case of the weak interaction? This is an interaction which occurs between electrons, neutrinos, and even quarks. And it is mediated by the Z node, the W plus, and the W minus bosons. The problem, however, with weak interaction is, as you know, these gauge bosons, the Z naught and the Ws, are extremely heavy. So they explicitly break gauge invariance. So it sounds like nature is playing trick with us, and that maybe gauge invariance is not such a fundamental symmetry. But fear not, young Padawans, because spontaneous symmetry breaking and the Higgs mechanism are here to save us.